right, so this week we have a test, and what that means is later today I'll put up a review. In general, the test will start with the word problem from the optimization section, because there wasn't one of those in the test. Other than that, it pretty much is mostly chapter 3, but could also have one from 2.8, which we skipped, which we will do before we get into section 3.11. Maybe. In some ways, we'll figure out if 2.8, so 2.8 and 3.11 are the last two things that could be on the test, and we'll find out today and tomorrow if they really are, because we'll see how far we get. We should be able to get through them, but we'll see. So remind me tomorrow to let you know if you can ignore anything on the review. And then later tomorrow, I'll put up the answers to the review. And then since there's a test on Thursday, we don't do anything new on Wednesday, except again, the usual, maybe a quick, like the other test, maybe a quick example on something that isn't on the test, just to keep it in your mind. So there might be 5-10 minutes of stuff at the beginning. Okay. All right, so we are in chapter 3, and in some ways a lot of the sections blend together. But let me look at first homework. So we're in 3.4, or we haven't done homework at least for 3.4. So let me remind myself what the actual question is. So 18 says, to integrate the given function over the given region. So here it's saying f of x, y, z is given by this. That's an x squared plus y squared. So we want to integrate the function 12yz over the region bounded by the cone, actually the half cone, z equals square root of x squared plus y squared, and the plane z equals 5. And let me draw the couple things. You don't have to draw the three-dimensional thing on the test, although it's probably not a bad idea for you to at least get an idea of it and then give the projection. But I won't take anything off if you don't show those, unlike the two-dimensional one, where I assume you can draw two-dimensional stuff. Okay, so cone is the straight lines. And then we have the z equals 3. So here we could project in a couple ways. If I project into the xy plane, what we'll be seeing is basically what we see from the front also. So if we project into either the xz plane or the yz plane, we're going to get triangles. Z equals 5, yes. Oh, yeah, so I forgot. I forgot if the homework actually might have said 3, but I didn't want to deal with square roots of 2. Oh, no, it is. This one I didn't change. So yeah, z equals 5. So now we want to project into one of the coordinate planes. So either the xy plane or the yz plane or the xz plane. And you can see that from what I've just drawn, that if I projected it into the yz plane, I'd be getting at the triangle. But then I would have to look at the front and the back functions, and those I'd have to solve for x in terms of y and z. And so I'm going to be lazy and project it into the y-plane. And so looking at this from above, what do I get? Yeah, I get the circle. So I just put in z equals 5. So I'm going to get the, I didn't give myself enough room. And that's not a very good circle. Sorry about that. And I'll square both sides. So I get 5 is equal to the square root. So x plus y squared is 25. So again, because we haven't done many, I'm going to split this up into 2 parts, but you won't have to for the test. So the first part is just, I'll leave the first 2 alone. And what I'm looking for here is what is the bottom curve and what's the top curve. So here, what is the, well, we'll start with the easier one. What is the top curve? Right. Oh, 5. Yeah, I'm not sure why I'm running a 3 there. Thank you. Now I can see why a few people asked me that. And the bottom curve is, right, the cone. Okay. So given how this is written, well, first I notice I actually tell you, but this is one of the ones that comes up a decent amount, especially once we get into spherical. So you'll kind of want to know if that's a cone. That's going to come up somewhat. So in some ways, I left it as dA just because for now we haven't decided if we want dy dx or dx dy. It doesn't matter. So I left it as dA so that we can decide in a second. I'm going to do dz dy dx, but we don't have to. In particular, now that I say it, I'm not going to. So given this function and given the projection, what coordinate system should we use? Right, polar. Or going into the next section, this will become cylindrical. So we have the 2 things. So given this, what are the, and let me bring over here because I'm going to need more room, dz, make it dr d theta, and bring in the r so I don't forget. What are the limits for theta? Oh, so give me, I think I said r, but yeah, so 0 to 5, and then 0 to 2 pi because it's all the way around the circle. What do the limits for z become? Right, so the top stays as 5, bottom x squared plus y squared is r squared, so we get r. And obviously the 12 stays as it is, the z stays as it is, and y in polar coordinates is r sine theta. And so that would be the whole thing. Okay, so again, this is the basic idea of what we do for triple, which is first we look for the smaller to the larger. And if we do zz, that means the bottom and the top function. If we did dy and the other 2, then it'd be the left and the right. If we did dx and then the other 2, then it'll be the back and the front. What I'll probably do is, I think I did this on one of the double integral ones, is mostly have you set up, but then have one where you actually go all the way through all the steps. And for that one, I'll probably give it to you. That way it makes it easier to grade because everyone at least is starting with the same thing. So probably on ones like this, I'll just have you set up and then separately have you do one all the way through. But there's no reason I couldn't do both. No, as I said, it's not a bad idea for your projection, but you don't have to. Oh, the function? No, so the 3-dimensional one you do not. Although, as I said, it's not a bad idea to see it because you can then see what's the bottom and top function. So any other questions on this? Okay, so I do 20. I should say that I think the early ones do ask you to draw. You will not be asked to just draw something. So 20, similar thing. We have a function. This is the one where I changed it. E to the y, yes, thank you. Sorry about that. So in this one is the one where I actually did change it. In the text, it had z equals 3, which will make it so that when we solve for x's, we're going to get square root of 2's. So I'm going to make it z equals 5, so we get integers instead. Not that it matters too much. So we have z equals x squared plus 1. And so I can try drawing it. So there's y equals x squared plus 1. It's just y equals x squared, z equals x squared plus 1. And then since y isn't in the function, it just is the whole planar type thing going across. And then we have, at the top, we have z equals 5. So we have a cover. And we make a cut at 1 and 2. So I'm not going to try drawing those, but we're making 2 cuts. So here there are 2 fairly easy projections. So let me actually do 2 projections here, which is I can project it into the xz plane. Let me bring this up so I can put the x's there. And then I can also project it into the xy plane. So let me do a couple of them here. So if I project this into the xz plane, what type of thing do I get? Just a parabola, right? So if I do xz, I get that. So let me do that one. Yeah, I might need more room with this, okay? So e to the y. So if I project into the xz plane, what variable do I start with? So dy. I forgot the top. Well, so it should be one that isn't one of these. In some ways, one of the ways you get what you start with is which variable we've lost. So therefore, it should be dy. And then the other two don't matter. Since I've drawn it with z as the replacement of the y, I'll do dz but it doesn't really matter. So that's that middle one's supposed to be a z. Sorry about that. So now, since we're doing it starting with dy, what we're looking for is what is the left. Well, I will in a second. So I'm saying that we can actually do this in two ways. So you can see this projection is fairly nice because now but here, what is the left curve and the right curve? It's easy, right? Just 1 and 2. And now we're into this picture. And so the bottom and the top curve, the bottom curve is x squared plus Well, so the whole function, right? So this whole thing. So x squared plus 1. So z equals x squared plus 1, and the top is 5. And for the outside one, now this is why I changed it. We need to know what the values of x are, which is this is -2. So -2 and 5, and 2 and 5. So this is -2 to 2. So that's what I get if I project into the xz plane. What do I get if I look at it from above? So if I project it into the xy plane, what does that look like? Right, looks like a rectangle. In particular, I don't even really have to draw it much. It's y is going from 1 to 2, and x is going from -2 to 2. So we're just getting something like this. And then using that one, I still have the e to the y, but now I do it dz, say dy. Sorry about the extra. Extra line. So now, since I start with dz, now I'm looking for what is the bottom function, what's the top function. And you can see this one, something happens where on the two-dimensional ones, I said you shouldn't assume is true. But here, the bottom limit for z would be just the bottom function, which is the x squared plus 1. And the top is, again, 5. And then y goes from the 1 to 2. And the x goes from -2 to 2. So we just reverse the order of the integrals, which in general you can't do, but sometimes like this, where we get rectangles involved, it does work. Notice we don't really want to do it into the yz plane, because although it's not too terrible, but in that case, we want to solve for z, in which case we'd have to solve for z, so we get x is equal to plus or minus the square root of z minus 1 for the limits, so there would be a bit messier. So as with the two-dimensional, you can do it whichever order you want. For me, I usually do it where it's the easiest one you can see the projection. So here, either of these for me is pretty easy. So for me, starting with dy or dz are both pretty easy. Projection into yz is also pretty easy. It's also a rectangle. But the functions we get are a little bit more complicated because we're going to get square roots. So in theory, any order is okay. In practice, since they don't do very many complicated ones, you can pretty much always do dz, dy, dx. Oh, I think I do one in a second, where you want to. But any other questions on this? So those two that I wanted to do. Most of the other ones, they pretty much give the order and just ask you to do the integral. But any other ones, this is 3.4 that you want to look at. So as I said, they pretty much give you the limits. Y goes from -2 to 1, -1, -1. Z goes from 0 to pi over 2, and x goes from y to 1. So in theory, we can do this any order we want, but unless we want to redraw it to see what this picture looks like so we can reorder it, which variable do we not want to be the outermost one? X, right? Because x, we have the limits in terms of y, which means it can't be the outside integral because the outside integral limit should always be constants, which means this has to be one of the inner ones. In particular, it needs to be before dy. So give some room to put in things. So y has to be after x, but other than that, any preference for the order? So we can either start with dz or dx. Doesn't look like it matters much. X, okay. And then, again, doesn't really matter. See, sure. Okay, so now we can just write in, because it's given y to 1. X goes from, z goes from 0 to pi over 2. And y goes from -2 to -1. So here, obviously, the y squared is just a constant. So it's just going to stay there. What's the antiderivative with respect to x of cosine of xz? So it's a little substitution where you let u equals xz. The derivative of xz with respect to x is z. We don't have it, so therefore we're going to get something like so when I plug in 1, I get I can see why. Take a second, so is it? I see. So as I say, this is not not going to be very nice because this there is supposed to be a z here, which which means this cancels, which means that cancels, and that cancels. I'm not sure why I made that z squared anyway. Okay, so that's a bit nicer. Okay. And it also makes this a little bit nicer. So the antiderivative of y squared z with respect to z is just the minus y squared cosine of z. And the antiderivative of sine of y over z is, I'm going to lose one of the y's. So if I put in pi over 2 into the first term, I get zero. And in the second term, I get see if I mess this up again. That. If I put in 0 into the first term, I get the negative y squared, so negative y squared, so positive y squared, and then minus positive y. So I get that. So these two obviously are pretty easy. How am I going to have to do this first one? Right, so I'm going to have to do a integration by parts type thing. So I'm not going to give you an integration by parts in the test. So the question is, do you care? Do you want to actually see this? Anyone that wants to, I guess? Okay. So I'm not going to make, no, certainly not partial fractions. Substitution, yes. So for example, here we used a simple substitution, right? Because we had the inside u is equal to xz. So du is equal to, with respect to x, is z. So therefore, we got the 1 over z cosine of u du type thing. And then the z's canceled. So substitution, yes. I'm not going to make you do integration by parts in the test. And certainly not partial fractions. Okay, so in some ways I can see why you want to look at it, because it is kind of a pain. So any others from 3.4? 16. Okay. So the first thing it says is actually do the integral, but then it says sketch the projected region, which you should be able to do, and then by hand or technology, do the solid. Solid you certainly will not have to do for the test. But let's do at least the projected region, which we get from these two. So since we're doing dy dx, we're going to get the xy plane. And we do kind of the same thing that you would have done on a quiz, which you graph everything. So you have y equals e to the x, which is there. We have y equals e. And from 0 to 1, and notice this is 1e, this is the region that we're integrating over. So here we don't really have to do it, but you should be able to graph the two-dimensional stuff. So I might make you do graphs of two-dimensional stuff, but not three-dimensional stuff. And then if you did want to graph the three-dimensional thing, as I said, get a three-dimensional grapher either using an app on the phone or just go on regular computer. But you wouldn't have to. So here it actually isn't too bad. Z equals y is just, if you forget the x for a second, it's just the line, z equals y. So just the one at the 45-degree angle, and then just that's a plane if you bring that out in the x direction. And so we're going to have the two things. So we're going to get it from the front. We're going to get a triangular region. And so looking above this, or kind of above and below this, we're getting triangular regions, planes coming out. But I cannot draw that. So actually doing it isn't too bad, I think. We'll find out. So the antiderivative of, oh, interesting. Oh, okay, it makes sense. So actually this is a really easy one. That's a 1/2 z squared. So if I plug in y and then negative y, what am I going to get? Careful. So we're going to get 1/2 y squared minus 1/2 negative y quantity squared, which is 0. And in some sense, you can kind of see why this would be. So we're doing z, and z goes from negative y. So if I was looking at this above it, I'd be having a line that's coming up out of the front, and then in the back, a line going out the back, one above the xy plane, and one below the plane. So therefore, the volume above and the volume below will be the same. So the whole thing just simplifies nicely. So that's just saying that volume above the xy plane is equal to the volume below the xy plane. Okay. Any others? Okay. So let me do one from 3.5. And I'll ask about the homework tomorrow, because remember 3.5 is volume. So in some ways, 3.5 should have been done before 3.4, because in 3.5 we're integrating a function over a solid. In 3.5 we're getting the volume of the solid, which means we're just going to integrate 1. So the only difference between 3.4 and 3.5 is we integrate over the three-dimensional integral. In 3.4, a general function, 3.5, the number 1. So it's actually easier. This one I also could switch if I want to make it nicer, but I decide not to for some reason. So here we want to find the volume of the solid bounded by z equals x squared plus 1. So actually similar to the picture I did before to some extent. So it starts the same way. So we have the parabola and then parallel to the y-axis. And then we have y equals 2, which is, let's say, just right here. And z equals 2y minus 1. And this I can't draw very well. So this is z is at 2, at y equals 2, 2y minus 1 is 3. So let me make that line z equals 3. So we're then going to get, if I draw this, 2y minus, that's almost, I suppose I should make that into a thing, into a dotted line for part of the way. And kind of a plane there. No, so in some ways this one is showing about as elaborate as we get. The only thing you need to sort of see from the picture in this is that notice the plane does not hit the paraboloid in the xz plane. So if I project this into the xz plane, what is it going to look like? The parabola. In fact, what I have right in the front there. So I'm going to get this thing, except z equals 3. I'm not sure what I'm making that y. And z equals x squared plus 1. On the other hand, the projection into the xy plane is a bit more complicated because at the very right, at y equals 2, it's all the way out to here. But as I'm moving down, it's getting less and less wide, so I'm not getting a rectangle. I'm getting some kind of triangular parabola type thing. I can't picture it real nicely. So in this case, you really want to project it into the xz plane. And if I do that, so since I'm projecting xz plane, I want to start with dy. What is the right function? So the left function is and let's do this dy dz dx, since I projected the way I've drawn the projection. So you can kind of see, not easily from my picture, but we have the plane here on the left. So we have to solve for z equals 2y minus 1 in terms of y. So we get 1/2 z plus 1. And on the right, it's easier. Y is equal to 2. And now here I skipped a little stuff. I said it, but didn't actually write it, which is here to see that this is the line y equals 3. What we did was, well, it was where these two crossed. So if I put y equals 2 into z, I get z is equal to 2 times 2 minus 1, which is the 3. So that's how I knew that was z equals 3 there. So now I look at my two-dimensional picture. What's the bottom curve? What's the top curve? The bottom curve is volume. I'm not sure why I'm putting a x squared here. Just the 1 there. Someone would have reminded me in a minute. So the bottom curve here is and then we'll have to get these points. Right, x squared plus 1. And the top is 3. And now just, what is this point? And then the other side will be this, the positive version. Right, square root of 2. So this will be negative square root of 2 to square root of 2. Okay, so any questions on this? Oh, so that's this point. Right, so we put in z equals 3 to get 3 is equal to x squared plus 1. So any other questions? Oh, sorry. Right, so since we projected into the xz plane, that meant we did dy. So whichever plane we're projecting into, we start with the one variable we're missing. So if we did it into the xy plane, we start with z. We start xz plane, we start with y, and so on. So any other questions on this? Oh, because we're looking for the volume. So to get the volume, we integrate 1. That's the only difference between 3.4 and 3.5. 3.5, when we're looking for the volume, we always integrate 1. Which means, in theory, we could actually do it with a double integral. Because it's just the double integral of the top curve minus the bottom curve. Or in this case, the left curve minus the right curve. Okay, anything else? So as I said, since this really is similar, I'm going to save other ones for tomorrow. So I'm not going to ask if you have other ones you want to look at from 3.5, but remind me to do that tomorrow. Okay, so let's get into 3.6. And I've been cheating a bit, which is that I have been using cylindrical coordinates all along. See if I can actually spell it. Which is what we're going to do is when we have 3 variables, we're basically going to let 2 of them be polar coordinates, and then the third one is just left as it is. So we've done a few of these. So I'll do one in a minute, but this we've already done. As I said, I've cheated a little bit, which is did this in 3.4 and 3.5. Spherical, we actually will have to talk about a little bit. As the name implies, spherical coordinates is what we want to do is to replace the coordinates when we have something that's spherical. So let me look at a typical point, and I can't draw this very well either. So here's the usual rectangular coordinate system. And we have a point x, y, and z. And what I'm going to do is similar to what I do in polar coordinates, which is I'm going to rewrite this in a different way, which is first I'm going to ask how far is this point from the origin. That I'm going to call rho, which I'll write in a second. Then I'm going to, and this is the part I can't draw very well, project that line that I just drew into the xy plane. The angle from the positive x-axis will be the same as my usual polar angle, theta. And then going from the positive z-axis, going down, I'm going to get another angle called phi, which I'll write in a second. So this will be equal to rho and phi and theta. And so one of them is pretty obvious in our conversion thing, which is that we have x squared plus y squared plus z squared is equal to rho squared. I should say this is a rho, Greek letter. And from the polar coordinates, we do have this transition part, which is we still have x is equal to r cosine theta, y is equal to r sine theta. And now I just have to get rid of the r and the z. So looking at my little triangle here, and this look like it because of the projection, but that's a right triangle. And let's make one here, probably better. So this is the phi. And again, my picture isn't very nice. So since this is r, this length is also r. So what is r in terms of rho and phi? This, of course, is z. Actually, I can start with that one. What is z in terms of rho and phi? And let me actually bring it down here, which is here's our little triangle. And make it look a little bit nicer. So that's phi. This is rho. This is z. This is r. So what is z in terms of the other two? Right, so z is the cosine. So it's going to be rho cosine of phi. And after I do the other one, I'll write down how you spell that Greek letter. And then what is r in terms of it? Just the sign of it. So that's the Greek letter phi. So we have this conversion, and then between these two and this, we get the other two conversion, which are kind of annoying. It's r cosine theta, where r is sine theta. Oops, and I lost a row there. So I'm going to get rho sine of phi cosine of theta. And y is equal to rho sine of phi sine of theta. And there's our conversion. Okay. And the extension. So remember when we do polar coordinates, we get the dy dx becomes r dr d theta. So the question is, what does dv become? And the way I always remember is, again, in two steps, which is kind of a guess that it might be something like this. I'm not going to try to show it, but the rho times the r, and therefore, since r is equal to rho sine theta phi, this is what the dz dy dx becomes. So in polar, we get the extra r. In cylindrical, we get this whole extra rho squared sine of phi, which is rho times r. So this is all the background. So let me now do a couple. Because we don't want r anymore, right? Our new variables are rho and phi and theta. So we have the r cosine theta, but we have to get rid of the r. So we substituted what r was to get rid of the r, because we don't want that anymore. Same thing here, which is we have an r, but there is no variable r. So I have to get rid of it. Oh, that's because I forgot it first too, so then filled it in. Sorry about that. So let's do with a really basic one, what it's designed for, which is let's integrate in some ways, same thing what I do with the circles. When I say sphere of radius 3, unless I say otherwise, I assume it's centered at the origin, because otherwise it gets to be a messier equation. So in other words, we have the x squared plus y squared plus z squared is equal to 9. So since this is what spherical coordinates are made, you should be assuming that, oh yeah, everything's going to be constants. And so this is just the one little thing. So first, the z becomes, that's supposed to be a rho. This. And then we always get the rho squared sine of phi. And then the d rho, d phi, d theta. And I should say over the solid sphere, because otherwise the sphere is just a surface. So the solid, not just the outer part. So part of it is pretty obvious. So just like with the polar coordinates, rho is going to go from 0 to 3, the origin to the outside. What is theta going to go from? 0 to 2 pi. And the reason I left off the middle one is now you have to think about this a little bit, which is suppose I have something, and let's make it phi is equal to pi over 4. So here's measuring down from the top. Here's equals pi over 4. But if I have that and then have nothing else, then notice I'm getting the whole thing. And I'm rotating it all the way around, and I'm not sure why I'm drawing. Actually, no, I am. So I'm getting that whole thing. So this starts at 0, but where does it end? And so in some ways you should be guessing not 2 pi, because otherwise I would have just put that in. So what's the upper limit going to be? Well, so pi 4. No, I mean, so here, so this is a complete aside. I'm just saying if it's pi over 4, we're going to get this whole thing. But for the full sphere, I'm not sure, I can't draw it like that. We're getting that. We're going to get 0 to pi. Because think about 0 to pi over 2 would bring you down to the xy plane. So that would be half of the sphere. and then we go all the way down to the bottom, we're going to get the whole sphere. So this one is a little bit different because it's giving us the whole sphere. So in the whole sphere, we're getting 0 to r, 0 to pi, and 0 to 2 pi. Right, it's always going to just be, the phi is just going to be from 0 to pi, right? And half sphere will be 0 to pi over 2, so it's a little weird. Right, so half sphere will be 0 to pi over 2. That would be the everything above the xy plane. No, because, for example, I could say we're doing, suppose I did this. D phi d theta. What would that give me? So I can certainly have that. So this, right. So again, it's kind of a weird thing to say it. This part says we're going all the way from the positive z-axis to the bottom z-axis. In some sense, we're getting a full sphere, but this is saying no, but we're not going all the way around the circle. So if I was looking at this for the projection, I'd be getting that. So again, half a sphere. So they are independent. Well, so in some ways they're the two half spheres, which is, so this would be one half sphere. And this would be another half sphere. So this would be the half sphere where we're looking at the half at the top. This first one here would be the half sphere where I'm looking at the sphere on the side. And if I want the sphere in the front, then it would go from kind of a weird way, from pi to 2 pi, or 0 to pi, one of those. So yeah, pi to 2 pi. So you can see there are a few ways I can talk about a half sphere, so the angles are going to depend on that. So there's some relationship, but in general, they're separate from each other. Okay, so let me do one more. This is the next easiest type of thing for spherical coordinates, and you'll see why in a bit. So we want to do the between the sphere and the cone. And in some ways, if you do this, so if I looked at this from the front, it actually does look like a cone. So if I look at this from the front, the cone is, of course, just this. I'm not sure why I'm drawing that. And the sphere looks like that. So it really does look like, kind of like an icon. So similar to the polar. So polar, you might want to use it if circles are involved. You might want to use spherical coordinates if spheres are involved. So here, it's possible that you might want to use it because we have spheres. So this one, as I said, doesn't look obvious, but this ends up being also quite nice in spherical coordinates. So let's actually redraw it. So z is equal to, so that goes to z is equal to rho cosine of, phi. What is this x squared plus y squared? Putting it into polar coordinates. Okay. And we know that is rho sine of phi. So the rho's, of course, cancel. And I can bring the cosine to the other side, and it just gives me tangent of phi is equal to 1. In particular, it gives me phi is equal to pi over 4. In theory, this, again, is just a half cone because the full cone is z squared is equal to x squared plus y squared, which would be the part above the xy plane and also the part below it. But if we're just looking at the half cone like here, cones are really simple in spherical coordinates. They're just a given angle. So I said, I changed the spherical coordinate. So z is equal to rho cosine of phi. That's a phi, not a rho. And then x squared plus y squared, I know in polar coordinates would be squared. So that becomes, so this is direct just from the spherical coordinates. This is me being intermediate, which is if I change this into polar coordinates, x squared plus y squared is equal to r squared. And of course, square root of r squared is r. And then this is, again, going from r to here is, again, just the definition, the conversion factor to spherical coordinates. So I could have gone through straight to spherical and said this is the square root of rho squared sine of phi cosine of theta plus rho squared sine squared of phi sine squared of theta. Notice that that simplifies to something to rho squared sine squared of phi, and the square root becomes rho sine of phi, but I went through r instead. So it's conversion where I went through polar coordinates. So the cone is the second most simple thing. So you'll see a lot of this on things where we want you to use spherical coordinates. So cones are nice in spherical coordinates, almost as nice as just spheres. Right? Because the sphere in spherical coordinates would be just something like rho is equal to 1. So let's do this again. So first, the x squared plus y squared plus z squared becomes, again, our conversion. That's rho squared, the radius of the sphere. And then, as we did with the last one, like the extra r we usually get, we get the extra rho squared sine of phi as part of the dz dy dx. And here you can see this is nice, which is it's a arc. So therefore, what are the limits for rho? Yes, x squared plus y squared plus z squared is always rho squared. So what are the limits for rho? Right, 0 to 2. What are the limits for phi? We know one of the limits is pi over 4 because we just got it. What's the other limit? So this is this is what you get when you change dz dy dx into spherical coordinates, right? And this is 0 to pi over 4. So here, what you have to think about for a second is we're always measuring phi from the positive z-axis. So we're, in this case, starting from the z-axis, which is 0, which looks a little weird at first. And then what are the limits for d theta? And that comes from this part. So since we're only in the first octant, right, 0 to pi over 2. So in 2 dimensions, right, we have the 4 parts, and they're labeled first, second, third, and fourth. In 3 dimensions, the 3 axes split into 8 pieces. So in some ways, there are 8 regions, which we could label 1 to 8. But as far as I know, pretty much the only one that's labeled is where x and y and z are all positive. So the first octant is, and I can't draw it well, but in this region where x and y and z are all positive. And then what happens to z squared? Well, it's the whole thing. So this whole thing becomes rho squared. Right. So rho squared is equal to x squared plus y squared plus z squared. Okay, so any questions from this? So at this point, I was actually going to do one where you try some on your own, but it's late enough that I think I'm going to wait until tomorrow to do that. So at the beginning tomorrow, we saw it. So for tonight, you're going to be looking at the homework for this section. But let me look at the next section, because 3.8, the next section, is again, in some ways, nothing new. And so I just want to do at least one example showing that there isn't really new. So any more questions on this? Spherical coordinates take a little time getting used to. Right, so cylindrical is just where you have, so in some ways where you have cylinders. But we did example, the reason I didn't do examples is we did some last week. So pretty much when we project and we get a circle, we're probably going to be using, actually, I think we did one today. If you do a projection and you're getting a circle, you're probably going to want to use polar coordinates, which means officially you're using cylindrical coordinates. So you use cylindrical coordinates when your projection is circles. And I think I'm going to do one in a second. Yeah, I'm looking at my notes, and I'm going to do one of those in a second. Oh, so here I had, I was trying to save space, but we had rho cosine of phi, and this is an equal sign, is equal to rho cosine of phi is equal to rho sine of phi. So you can see the rho's are going to cancel. And then I just divided through. I divided cosine for both sides. So yeah, I'm sorry about my messy writing here. If I was in class, I'd erase things and rewrite it, but it's hard to do that here. Any other questions on this? So let me actually do a cylindrical one, but as an intro into the next section. Okay. And in some ways, there's just the one quick idea, which you should have had from Calc 2. And otherwise, again, it's just like the others. So from Calc 2, if I give you a density, how do you get the mass? Or let's assume density is a constant. If density is a constant, how do I get mass? Right, so then there's the fuller answer. So if it's a constant, mass is equal to volume times density. If it's a function, or b or whatever we want. So I'm being kind of on purpose vague here because it'll depend on how many variables we want. But in general, mass is the way you get mass is you integrate the density over the region. So here's an example. And this is the Greek letter delta. So the solid cylinder from 0 to 2 has a density given by that, z times x squared plus y squared. Let's find the mass. And you can see that once we get this idea that what we're going to do is just integrate that function over the region, it's just like 3.4. I want to integrate a function over a region. Well, here the function is the density. So one of the ones I can sort of draw. So there's the cylinder. Obviously, I've made this an easier one. So let me start this one. So here we're going to do over the region we get, which you'll tell me what it is in a second, of the projection. What are the limits here? Z goes from where to where? Right, 0 to 2. And what's the projection? Oh, 0 to 2. What's the projection? Into the xy plane? Circle. And in particular, exactly what we started with. The x squared plus y squared is equal to 9. So what type of coordinate system do we want to use here? Polar, which means officially we're doing cylindrical because we're using 3 variables. And you can see we're doing a cylinder, which means we're using cylindrical coordinates. So really cylindrical coordinates is nothing new, it's just we're leaving one of the variables as it is. So looking at the projection, this is 0 to 2. What are the limits? So we're going to get the r dz dr d theta. What are the limits for r? 0 to 3. And the limits for theta will be 0 to 2 pi. Z we're not changing. What does x squared plus y squared become? R squared. And so that would be our integral. So you can see, for cylinders, cylindrical coordinates is again going to give us something easy where all the limits are constants. So officially, this is cylindrical coordinates. So as I said, I cheated. We've been using this for a week or so. And again, nothing really different than 3.4. It's just that in particular, the function we're looking at is the density, which means when we actually do the integral, we're going to get the mass. Okay, so any questions on this? So let me actually do one similar because I don't have the picture. So let me do another one which has a cone. And so we'll do a mass one. And we'll talk about it in that context. So any questions on this before I erase? Okay. So let's do and that's a 2 in front of the square root. So the region between the sphere of radius 4 and the cone z equals 2, x squared plus y squared, has density and let's make it fairly simple, just something like z. Oops. Not sure exactly what I do to make it do that, but there we go. So again, let's start with this. Let me start with this so I have everything here. Let's rewrite this in spherical coordinates because pretty obviously we're going to want to do spherical coordinates. So I rewrite everything. Z is equal to rho cosine of phi, which the right becomes 2r in my transition. I always do the transition, but you don't have to once you remember it. And then I remember that r is equal to 2, and then the rho sine of phi. So I divide both sides by the rho and the cosine of phi, and bring the 2 to the other side. I get 1/2 is equal to tangent of phi. And that's nothing nice. Phi is equal to whatever that is. So again, cones are nice. It's just phi is a constant. So if I drew this from the front, I might get something that looks like that. Fronts, yes. Yeah, cones are nice in spherical coordinates. So from the front or the side or whatever looking at, so for pretty much any side, if I look at it, it's going to look like that, where this is the sphere, the x squared plus y squared plus z squared is equal to, in this case, 16. And this is the phi is equal to tan inverse of 1/2. Okay. So I rewrite the z. Rho cosine theta. I get the thing that's always there for spherical, the rho squared sine of phi. And now again, work our way out. So what would be the limits for rho? Zero to 4. And you can see the reason it goes from there is, since I'm doing an arc, if I look at any line out of the origin, it doesn't hit anything until you hit the sphere, which means it's going all the way from 0 up to the outer level of the sphere. If we had something more complicated, like we did with the polar coordinates, where I did a straight line, so if I had, for example, x equals 1, that plane, then in that thing, the radius would be changing as I move along the surface. And so I'd have to get rho in terms of phi or theta or something like that. But cones are nice because it's an arc, which means you're getting the full line from the origin to this sphere. And then here, phi would go from 0 to what we just found. and theta goes from 0 to 2 pi. So again, nothing really new from this section, except for the idea that since I actually never said it, but if we want to find the mass, what we integrate is the density function. Oh, because notice there's no restriction, so if I was drawing it, you'd be the whole thing around it. And we're going all the way around. So if I project this, I'm getting the full circle. And so therefore 0 to 2 pi. In some ways we'll find out tomorrow, because tomorrow, if we get done with something early enough, it could be on the test. So definitely it will be the word problems from optimization section, and definitely through this, so through 3.8. And the question is, after this tomorrow, we'll go backwards, go into 2.8, and at least start 3.11. So those I'm not sure about. So definitely the word problem for optimization, definitely 3.1 through 3.8. I think we skip 1 or 2 sections, but for the ones we do. So tomorrow I'll be able to be more exact, saying exactly what's going to be on it, because see how quickly we get through stuff tomorrow. Okay, so any questions on this? Okay, so we have the 10 minutes or so, the usual quick intro into the next thing, which is I skipped 2.8, but we're going to now need it for the next section, 3.11. So again, we're skipping sections. Which is parameterizing surfaces. And in some ways, we've done the basics of this already, which is to parameterize a function. Here's a function in kind of our usual way of doing it. Y is a function of x. Is I can parameterize by saying x is equal to t, and then y is equal to t squared. And so we get the parameterized function, f of t, and that's a variable, vector, is given by this. So there's the kind of the usual way of writing the function. Here's the parameterized form of it, or the vector form of it. And as was true when we first did it, there are a couple reasons you might want to do this. One is it lets us move along the path. We've introduced a new variable. We can move along the path and instead of just saying we have the curve, we can say, well, at time 0, we're at the point 0, 0. After 1 second, we're at the point 1, 1. So we can talk about moving along it. So we can talk about what's the velocity of the movement and so on. So we're adding a bit more dimension. It also allows us to graph some slightly more complicated things. So for example, if I had this, let me not say anything and just ask, and this part, as usual, we're not going to make you graph, so don't worry about it too much, just explaining why we might want to parameterize functions, is can you picture what this is giving us? And let me start with this part, which is ignore the t for a second. What are those first two variables giving us? If x is cosine t and y is equal to sine t, what is that giving us? A circle. So by introducing the z equals t, what's happening? Right, we're getting a spiral along a cylinder of radius 1. where in regular coordinates, that wouldn't necessarily be a function at all. We'd probably have to break it up into two pieces. So it allows us to draw more complicated things while leaving it as a function, and also allows us to introduce time so we can talk about moving along a path. And most of the stuff we're not going to use, but we'll use some of it. So that's why we might want to parameterize surfaces, to draw more complicated things and leave them as functions, and to introduce time. So let me look at one. Here's a sphere. And the idea is there's always an easy way to parameterize a surface if you really want to. So let me parameterize this. So now we have three variables, so now we're going to have to use, instead of just the one t, we're going to have to use two. So I'm going to let x be some variable, let's call it u, y be some variable, let's call it v, and then just solve for z in terms of the other two variables. So it's easy to introduce a third variable, or a fourth variable. Just let all but the last variable be the same thing, basically, and then solve for the last variable in terms of the others. Of course, that doesn't necessarily give the best one. Given this, what this is, how do you think you would really parameterize it? So it would be a better parameterization for this? What type of thing is that? So what is this thing? Right, so it's a sphere, so we might want to use spherical coordinates. So x is equal to the rho sine of phi cosine of theta. It's just that rho here is 3. So that's also a parameterization. And for a lot of purposes, it's probably a better one, although you can see it looks more complicated at least. So there's no one parameterization. There are often many of them. For us, going forward, about the only ones that you need to be able to do are just this boring one. Just let all but one variable be just basically its own variable, and then solve the last one in terms of it, or circles and spheres. Not much beyond that. How do you... So I'm not sure. How do you XYZ? How do you write XYZ, or what do you mean? So this x is equal to, in general, rho, but in this case, since it was a sphere of radius 3, so I'm not sure. So there they are again. So are you asking what? Yeah, I'm not sure what you're asking. Oh, so that's just the general one. So this is what we always have is in spherical coordinates. We always have x is equal to rho sine of phi cosine of theta. Y is equal to rho sine of phi sine of theta. Z is equal to rho cosine of phi. So it's just the general spherical coordinates, except since we have a sphere of radius 3, we know rho is equal to 3. Well, in this case, so as I said, most of the time we would give you, I was going to say just in a minute, but probably tomorrow, I would just give you a parameterization. So as we get into it, I'll remind you in a few times that the only types of parameterization you need to be able to do are the really basic one where you just let all but one variable be its own variable and then solve the last variable, or circles or spheres, which means you need to know polar coordinates, you need to know spherical coordinates. But as we're starting to use it, I'll remind you about all that stuff. So for now, I'm just saying that we can parameterize something in more than one way. Right, so let me get to the one thing that we need from this, which is, like most stuff, what we would like to be true is that the function we get is fairly nice. In terms of parameterizations, that's going to be called regular. A parameterization is regular in pretty much we want to do things in 3 dimensions. And write out how the text does. Is first we need it to be true on, and this is usually fairly straightforward, although it needs to be true in a fairly nice region. So it's non-empty, so obviously there's some points. They're not 2 pieces here and there, and it's open. That's usually fairly much always true, so you don't have to really think about that part too much. Second is main part. The parameterization of the 2 variables is continuously differentiable on W. And third one, which we'll need for 3.11, show that we actually do get 2 separate ones. We need the 2 derivatives to be linearly independent. And if you've done linear algebra, you know what that means, but let me put it here. And there are 3 ways to check for this part. One is that the only way you can get a linear combination to be 0 is if both the constants in front of them are 0, or in 2 dimensions the same thing. So this generalizes to however many variables you wanted. But since there are only 2, you can divide through and just say, well, there's no c, so that one is a constant multiple of the other one. Or, which seems like more work, but will actually be part of the problems we're going to be doing, so often we'll be getting this anyway, that their cross product is not the 0 vector. So in some ways, these are the 2 main things, which is the derivative is nice, and we get vectors that are linear independent. First one is usually pretty true. So let me quickly do one, and then we'll really deal with it tomorrow. So example, to show that there is some problems. So here's a half cone. let's parameterize it. And as I said, let's do the what we always do, which is I'm just going to let x be u. I'm going to let y be v. And then I'm going to solve for z in terms of the other two. So there's a parameterization. X is u, y is v, z is equal to x squared plus y squared, which is square root of u squared plus v squared. So let's take a couple partial derivatives. So the derivative. Yes, I'll write it down. So in some ways, I'll say the same thing I just erased, but now with this specific example. So let's take the derivative with respect to u. So obviously this is 1, this is 0. Oh, this is this is parenthesis u. Sorry about that. I thought you were talking about the last one. So the derivative of u is 1, derivative of v is 0. Derivative of this is the and you can check this, but this will just be the 2u and then times the 1/2. So I'll just get this. And then the derivative with respect to v will be the same thing, except we'll get v in the numerator. So let's ask if this is regular. And so two main pieces we need are, one is the derivative exists pretty much everywhere. And here there's one problem, and I want to do it. So where's the derivative not exist? Where is there a problem? Right, so if I put in u and equals v equals 0, because then we're dividing by 0. So at 0, 0, there's a problem. If we drop that off, then it is fine everywhere else. So that part is okay, except for at 0, 0. And the second part is we need to know, are they linearly independent? And so the easiest way is we need, is one a constant multiple of the other? And it should be pretty obvious that that doesn't work because I have 1 in the first entry versus 0 in the entry. So obviously I can't multiply by anything to make it 0 and at the same time go from 0 to 1 going the other way. So they are linearly independent. And what that means is we're getting 2 dimensions, which is what we're going to need. This is going to give us 1 dimension, this is going to give us another. So we're going to get 2 vectors that aren't parallel, essentially is what we're asking, because that way when we put them together, we're going to get a plane. We need a 2-dimensional thing. And that means since they're not parallel, when we take the cross product, we get a third vector. So this is similar. So if we take the cross product, if we don't get a 0 vector, that also would tell us that they're linearly independent. Obviously, that's more work, but as I said, tomorrow we'll see that in some cases we're going to want to take the cross product anyway. So might as well just do it as part of this. So they're not linearly independent, so this, no, therefore regular, yes. So they're, oh, so yes. So regular, yes, if we're ignoring the 0.00. So sorry, going over a little bit. So the usual quick introduction, so we'll really do this tomorrow. So for tomorrow, start looking at the homework for the 3.6 and 3.8. And tomorrow you'll remind me, as we're going through the class, what exactly, I'll remind you what's on the actual test. So later today I'll put out a test review, but it might contain stuff that isn't going to be on the test. Okay, so as usual, I'll stick around if you have any questions, but that then derivative exists everywhere else. Sorry about that. When I'm writing, it's trying to smooth things, so sorry about that. It doesn't like me writing. So let me stop recording.